Tonight, we're going to explore one of the most unsettling discoveries in the history of science. Not unsettling because it is dangerous, not unsettling because it threatens anything in our daily lives. Unsettling because it reveals that everything we have ever studied, everything we have ever touched, every atom of every planet and star and galaxy we have ever observed, every particle we have ever detected in every accelerator ever built, every measurement ever made by every instrument ever devised in the entire history of human science accounts for less than 5% of what the universe actually contains. Less than 5%. The other 95% is something else entirely. Something we cannot see, something we cannot touch, something we cannot detect directly with any instrument we currently possess. Something that does not emit light, does not absorb light, does not reflect light, does not interact with light in any way that we have been able to measure. Something that is, by every observational tool available to us, completely invisible. And yet we know it is there, not because we have seen it, because we have seen what it does, because the universe is behaving in ways it has absolutely no business behaving if everything we can see is everything there is. Galaxies spinning too fast, light bending too sharply, the universe expanding not at a decreasing rate as gravity should demand, but at an accelerating rate, pushed apart by something that acts like negative gravity, something that fills every cubic centimeter of space and pushes outward with a pressure that grows stronger as the universe grows larger. The universe is hiding most of reality, not from malice, not from any intention, simply because the universe contains things that are, by their nature, invisible to the particular instruments and senses that evolution gave to creatures like us, and that physics has taught us to build. We evolved to detect light, to feel pressure, to hear vibrations. We built instruments that extend those senses to extremes we never could have imagined. We built radio telescopes and X-ray detectors and gravitational wave antennas and particle colliders. And with all of them, we can access about 5% of what exists. The rest is hidden in plain sight, everywhere. Right here in the room, passing through your body at this moment in quantities that dwarf the ordinary matter you are made of, and we do not know what it is. 7 profound discoveries that reveal exactly how the universe conceals most of reality, what those concealments imply about the nature of existence itself, and why the fact that we have discovered our own ignorance might be the most important scientific achievement of the last century. Before we get started, if these questions about what we are missing, what the universe is not showing us, are the kind of questions that keep you thinking long after the screen goes dark, hit like or subscribe. It helps us reach more minds that want to sit with ideas like this. Now let's begin. The year is 1933. A Swiss astronomer named Fritz Zwicky is sitting with data from one of the most carefully constructed surveys of galaxy clusters ever attempted. He has been measuring the velocities of individual galaxies within the Coma cluster, a collection of more than 1,000 galaxies about 320 million light-years from Earth, one of the largest and most studied galaxy clusters in the sky. The measurement he is making is straightforward in principle. By observing the spectrum of light from each galaxy and measuring the Doppler shift, the stretching or compression of light wavelengths caused by motion toward or away from the observer, he can calculate how fast each galaxy is moving, and the answer he gets makes no sense. The galaxies in the Coma cluster are moving far too fast, not slightly too fast, dramatically too fast, by factors that cannot be explained by any reasonable accounting of the mass, he can see in the cluster. When Zwicky estimates the total mass of the cluster from the light it emits, adding up all the stars and gas he can observe, and then calculates how fast the galaxies should be orbiting based on that mass, the observed velocities are roughly 400 times higher than the prediction. At those speeds, with only the visible mass holding things together, the galaxies should be flying apart. The cluster should have dissolved long ago. It has no business existing as a coherent structure, and yet there it is, a gravitationally bound collection of more than 1,000 galaxies that has been together for billions of years. Zwicky concludes that the visible matter is not all the matter. There must be additional mass that he cannot see. He calls it dunkel materie, dark matter. The physics community largely ignores him for 4 decades. Then, in the 1970s, an astronomer named Vera Rubin starts measuring something slightly different. Not galaxy cluster dynamics, but the rotation curves of individual galaxies. How fast the stars in a galaxy orbit the galactic center as a function of their distance from it. And what she finds confirms what Zwicky found, but at a different scale, in a different measurement, using a different technique, on different objects. The stars on the outer edges of galaxies are moving too fast, much too fast. By Newtonian gravity and by general relativity, stars far from the galactic center should move more slowly than stars close in, just as the outer planets of our solar system orbit the sun more slowly than the inner ones. The gravity at large distances should be weaker. The orbital speed should decline. It doesn't. The rotation curves of galaxy after galaxy are flat. The speed of stars in the outer disk is essentially the same as in the inner disk. All the way out to the observable edge of the galaxy, the stars move at roughly the same velocity. This is only possible if there is an enormous amount of mass that we cannot see distributed through and around the galaxy in a diffuse halo extending far beyond the visible disk. A halo of something massive enough to maintain the flat rotation curve, something invisible, dark matter. Zwicky had been right all along. The evidence for dark matter has only accumulated in the decades since Rubin's work. It comes not from one measurement, but from many independent measurements using completely different methods, each pointing to the same conclusion. Gravitational lensing is perhaps the most direct. General relativity predicts that mass curves space-time and that light traveling through curved space-time follows curved paths. A massive object between us and a more distant source will bend the light from that source, acting as a gravitational lens. The degree of bending depends on the mass of the lens. When astronomers measure the gravitational lensing by galaxy clusters, adding up the total bending of light from background galaxies and using that to calculate the total mass of the foreground cluster, the mass they infer is many times larger than the mass they can account for in visible stars, gas, and dust. The invisible mass has to be there to produce the observed bending. It cannot be faked. It cannot be explained away. Light is bending around mass that we cannot otherwise detect. The bullet cluster is perhaps the single most compelling piece of evidence. The bullet cluster is the aftermath of a collision between two galaxy clusters. When the clusters collided, the hot gas in each cluster, the vast majority of the ordinary matter, was slowed and heated by electromagnetic interactions between the gas cloud. The galaxies themselves, which are mostly empty space, pass through each other without significant interaction, and the dark matter, not interacting electromagnetically at all, pass through the collision without slowing down. After the collision, the cluster shows a clear separation. The hot gas, glowing in X-rays, is concentrated in the collision zone, slowed to a stop. The galaxies and the dark matter halos are ahead of the gas in the direction of travel, having passed through the collision without being slowed. Gravitational lensing maps show the mass concentrated where the galaxies are, not where the gas is. The dark matter is visibly, measurably, separately located from the ordinary matter. This is not a hint. It is not a statistical tendency. It is a dramatic, spatially resolved observation of dark matter behaving differently from ordinary matter in a collision. And it behaves exactly as dark matter theory predicts. It is the bullet cluster that most effectively silences the primary alternative to dark matter. Modified gravity theories that try to explain the observations without invoking invisible mass. The bullet cluster shows dark matter and ordinary matter in different places. No modification of gravity can separate matter that is all in the same location. The cosmic microwave background adds another layer. The pattern of temperature fluctuations in the CMB, measured by satellite missions with extraordinary precision, encodes the acoustic oscillations of the early universe. The ratio of the first to second acoustic peaks in the CMB power spectrum is sensitive to the ratio of dark matter to ordinary matter. The measurements give a clear answer. Dark matter outnumbers ordinary matter by about 5 to 1. There is about 5 times as much dark matter as everything we can see in every direction throughout the entire observable universe. 5 to 1. For every atom of hydrogen and helium and carbon and oxygen and iron that makes up everything we have ever studied, there are 5 times as much of something else. Something that has mass, that exerts gravity, that shaped the large-scale structure of the universe, that is sitting in halos around every galaxy, including our own, and that we cannot directly detect at all. This is shocking discovery number 1. The universe hides 5 times as much mass as it shows. Let's be precise about what dark matter is not, because there have been many proposals, and most of them have been ruled out. Dark matter is not just ordinary matter that is dark. Not black holes from dead stars, not brown dwarf stars too dim to see, not cold gas clouds, not any normal matter in a non-luminous form. We know this from multiple lines of evidence. Big Bang nucleosynthesis, the process by which hydrogen and helium were synthesized in the first few minutes of the universe, produced specific ratios of light elements that depend on the total amount of ordinary matter present. The predicted ratios match the observed ratios only if ordinary matter makes up about 5% of the universe's total energy content. If there were more ordinary matter in any form, the nucleosynthesis predictions would fail. Dark matter cannot be made of protons and neutrons. It is not neutrinos. Neutrinos are real, abundant, nearly massless particles that pass through ordinary matter with almost no interaction. They are, in that sense, somewhat dark, but neutrinos move at nearly the speed of light and are what physicists call hot dark matter. Hot dark matter cannot form the structures we observe. It smears out rather than clumping. The universe we see has small structures forming first and large structures forming later, the hallmark of cold, dark matter that moves slowly. Neutrinos do not fit the bill, though they contribute a tiny fraction of the total dark matter density. It is not antimatter. Antimatter would annihilate with ordinary matter, producing gamma rays. We would see the signal. It is not a flaw in our theory of gravity. Modified gravity theories, including one called MOND and its relativistic extensions, have been proposed as alternatives. They work reasonably well for individual galaxies, but fail for galaxy clusters. They cannot explain the bullet cluster. They produce incorrect predictions for the CMB acoustic peaks. They have been tested and found wanting. Dark matter is something new, something not in the standard model of particle physics. Something that has mass and gravity and is cold, meaning it moves slowly compared to the speed of light, and is non-baryonic, meaning it is not made of protons and neutrons, and is collisionless or nearly so, meaning it does not interact with itself or with ordinary matter. through the electromagnetic force. The leading candidates are particles called WIMPs, weakly interacting massive particles, which would interact with ordinary matter only through gravity and the weak nuclear force. WIMPs are predicted by supersymmetry, a theoretical extension of the standard model of particle physics that proposes that every known particle has a heavier partner. The lightest supersymmetric particle would be stable and would have exactly the properties dark matter needs. The problem is that we have been searching for WIMPs in underground detectors for decades and have found nothing. The experiments have become extraordinarily sensitive. They have ruled out WIMP properties across enormous ranges of mass and interaction strength. The simplest WIMP models have been largely ruled out. More exotic versions remain possible but are increasingly constrained. Another candidate is the axion, a very light particle proposed in the 1970s to solve an unrelated problem in particle physics, the strong CP problem. Axions would be produced in enormous quantities in the early universe and could account for the dark matter density. They are extremely light, much lighter than WIMPs, and interact so weakly that they are extraordinarily difficult to detect. New experiments specifically designed to detect axions are operating and setting new limits, but no detection has been confirmed. There are other candidates: sterile neutrinos, primordial black holes, fuzzy dark matter. Each has specific properties and specific experimental signatures. None has been confirmed. Dark matter is the most well-established thing in physics that no one has directly detected. Shocking discovery. Number 2. The universe is mostly something else entirely. Dark matter, as invisible and mysterious as it is, turns out to be only 27% of the universe's total energy content. Ordinary matter is 5%, which means 68% of everything that exists is something that is not matter at all. It is called dark energy, and it is stranger than dark matter in every way. The discovery of dark energy came in 1998 from 2 independent teams of astronomers studying a specific type of stellar explosion called a Type 1a supernova. Type 1a supernovas are useful to cosmologists because they are standard candles. They explode with a characteristic luminosity that allows astronomers to calculate their distance from their apparent brightness. Observe the apparent brightness, calculate the distance, measure the redshift, calculate the recession velocity, build a distance-velocity relationship for the universe. The 2 teams, the Supernova Cosmology project led by Sol Perlmutter and the High Z Supernova Search team led by Brian Schmidt and Adam Rees, were both trying to measure the deceleration of the universe. Everyone expected the universe to be decelerating. Gravity should be slowing the expansion. The question was, only by how much? The rate of deceleration would tell you the density of matter and the ultimate fate of the cosmos. Instead, both teams found that the distant supernovas were dimmer than expected, fainter than they should be if the universe were decelerating, which meant they were farther away than expected, which meant the universe had been expanding faster in the past than their models predicted, which meant the expansion was not decelerating, it was accelerating. The universe is getting larger, faster with every passing moment. The expansion rate is not slowing down, it is speeding up. This was so unexpected, so contrary to all prior assumptions, that both teams spent months checking for errors. They looked for systematic biases in the supernova observations, for dust that could make supernovas look fainter, for evolution of supernova properties over cosmic time. They found nothing that explained away the result. The acceleration was real. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011 for this discovery. It is genuinely one of the most consequential observational results in the history of cosmology. Something is pushing the universe apart. something with a repulsive effect that increases as the universe gets larger, something that acts like a negative pressure, a tension in the fabric of space itself, working against gravity on the largest scale. The simplest description is the cosmological constant, a term that Einstein introduced into his equations of general relativity in 1917, and later called his biggest blunder. He had added it to make a static universe, the prevailing cosmological model of his era. When Hubble showed the universe was expanding, Einstein dropped the term, but the observations of 1998 brought it back. The cosmological constant, denoted by the Greek letter lambda, fits the data. It is constant in space and time. It fills every region of the universe uniformly, and it has exactly the repulsive effect needed to explain the observed acceleration. But what is it physically? This is where dark energy becomes not just mysterious, but genuinely alarming to physicists who think carefully about it. Quantum mechanics predicts that the vacuum of space is not truly empty. The uncertainty principle, one of the foundational principles of quantum mechanics, implies that the energy of any region of space cannot be exactly zero. Quantum fields fluctuate constantly, even in the vacuum. Virtual particle pairs appear and disappear continuously. These fluctuations carry energy, and that energy should contribute to a cosmological constant. When physicists calculate the expected energy density of the quantum vacuum, they get a number, a specific calculable number from well-tested quantum field theory. That number is approximately 10 to the power of 120 times larger than the observed cosmological constant, 10 to the 120, a factor of 1 with 120 zeros after it. The predicted value is unimaginably larger than the observed value. The discrepancy is the largest in the history of physics, the most embarrassing mismatch between theory and observation ever recorded. There is no other case in science where a well-established, well-tested theory makes a prediction that is off from observation by 120 orders of magnitude. Something is canceling out almost all of the vacuum energy. Some mechanism is reducing it from the enormous theoretical value to the tiny observed value with extraordinary precision, canceling it not perfectly, but to 1 part in 10 to the 120, and we have absolutely no idea what that mechanism is. This is the cosmological constant problem, and it is widely considered the deepest unsolved problem in fundamental physics. It sits at the intersection of quantum mechanics and general relativity, the two most successful theories in the history of physics, and it reveals that something is profoundly wrong with how we understand the vacuum of space. Dark energy is 68% of the universe. We do not know what it is. The best theoretical prediction is off by 120 orders of magnitude. The universe is not just hiding most of its content. It is hiding the nature of the fabric of space itself. Shocking discovery. Number 3, we cannot see the scaffolding that built everything. Long before the first stars lit up, the universe was dark. Not just dark in the sense of lacking light sources, dark in the sense that ordinary matter, the hydrogen and helium gas that would eventually become the first stars, was distributed nearly uniformly through space, with only tiny fluctuations of 1 part in 100,000. From those tiny fluctuations, in only a few 100 million years, the first stars and galaxies formed. Ordinary matter fell together under gravity, heated up, ignited nuclear fusion, and the universe lit up with the first light since the CMB. But ordinary matter cannot do this alone, not in the time available. The fluctuations are too small. The time is too short. Ordinary matter, subject to electromagnetic pressure that resists compression, could not have collapsed fast enough to form the structures we observe before the dark matter beat it to the job. Dark matter, not subject to electromagnetic pressure, began collapsing earlier. before the universe became transparent, before ordinary matter could collapse at all. Dark matter formed what cosmologists call the cosmic web, a vast three-dimensional network of filaments and sheets and nodes shaped by the gravitational interplay between dark matter halos with enormous empty voids between the filaments. When ordinary matter was finally free to fall under gravity after the universe became transparent at 380,000 years, it fell into the pre-existing dark matter scaffolding. It followed the grooves already carved by the invisible structure. Galaxies formed at the nodes where dark matter halos were densest. Galaxy clusters formed where the largest dark matter concentrations had assembled. The cosmic web of galaxies we observe today is a luminous tracing of a dark matter web that has been in place much longer. We can simulate this. Taking the initial conditions revealed by the CMB and applying the known physics of gravity, dark matter and ordinary matter, supercomputers can evolve the universe forward in time. The results, simulations called the Millennium Simulation and the Illustris Project and others, produce a cosmic web that is strikingly similar to the observed distribution of galaxies. Filaments, clusters, voids, sheets. On every scale that we can compare, the simulated dark matter web matches the observed galaxy distribution. We are living inside the scaffolding. The Milky Way is embedded in a dark matter halo hundreds of thousands of light years across. The local group, the cluster of galaxies that includes the Milky Way and Andromeda and dozens of smaller galaxies, is embedded in a larger dark matter structure. The Virgo supercluster and the larger Laniakea supercluster, the enormous structure of which our local group is a tiny part, are filaments in the cosmic web. None of this dark matter scaffolding is directly visible. It is inferred from the distribution of the galaxies it contains and from gravitational lensing. But it is as real as the galaxies it holds, and without it, those galaxies would not exist. This is shocking discovery number 3. The architecture of the universe, the scaffolding within which all visible structure formed, and within which all visible structure sits, is made of something we cannot see. Let's talk about what the universe's composition means for the broader project of understanding reality. For the entire history of science before the 20th century, scientists operated on the assumption, never explicitly stated because it was never challenged, that the matter we can see and study is the matter that exists. The universe might be larger than we could observe. It might contain regions we had not yet mapped, but it was made of the same stuff everywhere. Atoms, protons, neutrons, electrons, the periodic table, the stuff of chemistry and biology and geology, the stuff of everything. That assumption was destroyed in the 20th century. It was not a gradual erosion. It was a series of discoveries, each independently confirming that the visible universe is a minority constituent of the total. Dark matter was confirmed. Dark energy was discovered, and these two invisible components together account for 95% of the universe's energy content. The ordinary matter we spent centuries studying, the matter for which we developed quantum mechanics and nuclear physics and chemistry and every other branch of physical science, is an afterthought, a minor contaminant in a universe dominated by things we do not understand. This is either the greatest discovery in the history of science or the beginning of the greatest era of discovery. Possibly both. Because here is the thing. The 5% we understand is enough to have built civilizations, to have developed agriculture and writing and mathematics and art, to have launched spacecraft to the edge of the solar system, to have detected gravitational waves from black hole mergers a billion light years away. 5% of the universe is enough for all of human experience. Imagine what understanding the other 95% would mean. Shocking discovery. Number 4. The universe has a missing baryon problem. Even within the 5% that we can see, there is more hiding. Ordinary matter, the baryonic matter made of protons and neutrons, accounts for about 5% of the universe. We know this from multiple independent measurements. Big Bang nucleosynthesis tells us the total amount. The CMB acoustic peaks tell us the same thing from a different measurement. The two agree with each other precisely. But when astronomers add up all the ordinary matter, they can actually find and observe all the stars and gas and dust in all the galaxies they can see. They get only about half the predicted amount, maybe less. Where is the rest of the ordinary matter? It is hidden, not as dark matter, as ordinary matter made of protons and neutrons just like us, but in a form that is very difficult to detect. The leading candidate is a warm, hot intergalactic medium, a vast diffuse gas of ionized hydrogen and helium spread through the cosmic web in the filaments between galaxies at temperatures between 100,000 and 10 million degrees Kelvin. At those temperatures, the gas does not emit visible light efficiently. It emits primarily in the ultraviolet and soft X-ray parts of the spectrum, wavelengths that are difficult to observe because they are absorbed by our own galaxy's gas before reaching our detectors. For decades, this gas was essentially invisible to our instruments. Recent observations using fast radio bursts, bright radio flashes from distant galaxies whose signals are dispersed by the free electrons they pass through on their way to us, have allowed astronomers to measure the total electron content along lines of sight through the cosmic web. The measurements are consistent with the missing baryons being there, spread through the filamentary structure of the cosmic web. Even the matter we thought we understood is hiding in places we were unable to look until very recently. The universe conceals even its ordinary matter in forms and locations that require extraordinary instrumentation to find. This is shocking discovery number 4. Even the 5% of reality we thought we understood contains a hidden component. Ordinary matter spread through the cosmic web in forms that evaded detection for decades. Shocking discovery. Number 5. The universe's expansion. History is written in invisible ink. The history of the universe's expansion from the Big Bang to the present is one of the fundamental subjects of cosmology, and most of that history is dominated by components we cannot directly see. In the very early universe, the dominant component was radiation, photons, and neutrinos. As the universe expanded, radiation diluted rapidly, and ordinary matter and dark matter became relatively more important. For most of cosmic history, from about 50,000 years after the Big Bang until about 5 billion years ago, the universe's expansion was governed by the gravity of matter, ordinary and dark, pulling against the expansion and slowing it down. Then dark energy began to dominate. As the universe expanded, the density of matter decreased because the same amount of matter was spread over an ever larger volume. But the density of dark energy stayed constant. The cosmological constant, by its nature, has the same density everywhere and always. As the universe expanded, dark energy went from being a minor component to being the dominant one. 5 billion years ago, dark energy surpassed matter in importance, and the expansion began accelerating. This transition from matter domination to dark energy domination is written in the large-scale structure of the universe. During matter domination, gravity was powerful enough to form and amplify the cosmic web. Galaxy clusters grew, filaments thickened. During dark energy domination, the expansion accelerates and structure formation slows. The universe will eventually consist of our local bound structures, the local group and perhaps the Virgo cluster, isolated in an expanding void as all other galaxy groups recede beyond our horizon. But here is the hidden part. The transition from matter domination to dark energy domination 5 billion years ago is not directly visible. It is inferred from the expansion history, measured through supernovas and the CMB and baryon acoustic oscillations. The physics driving the transition is almost entirely in the dark sector. The dark matter that dominated before 5 billion years ago is invisible. The dark energy that dominates now is invisible. The expansion history of the universe is a story written by invisible actors, reconstructed from their effects on the visible 5%. The universe's biography is composed mostly in invisible ink. Shocking discovery. Number 6. Something is wrong with the measurements themselves. This is the newest crisis, and it may be the most important. The universe has two fundamental parameters that characterize its expansion: the Hubble constant, which measures the current rate of expansion, and the total energy content, which determines how the expansion evolved over time. These parameters can be measured in two completely independent ways. The first method uses the early universe. The CMB, measured with extraordinary precision by the Planck satellite, encodes the acoustic oscillations of the primordial plasma. Combined with a specific cosmological model, it predicts what the Hubble constant should be today. The answer is approximately 67 kilometers per second per megaparsec. For every megaparsec, roughly 3 million light-years of distance between two objects, they should be receding from each other at 67 kilometers per second. The second method uses the late universe, measuring distances and recession velocities to nearby galaxies using supernovas, Cepheid variable stars, and other distance indicators, and building up the distance ladder from our local cosmic neighborhood outward. This gives the current expansion rate directly, without reference to any cosmological model. The answer is approximately 73 kilometers per second per megaparsec. 67 versus 73. These numbers do not agree. The discrepancy is about 9%, and the measurements are both so precise that the discrepancy is statistically significant at a level that would, in most fields, be considered a definitive indication that something is wrong. This tension is called the Hubble tension, and it is one of the most discussed problems in modern cosmology. Both measurements have been checked and rechecked. The early universe measurement from the CMB has been independently confirmed by multiple analyses. The late universe measurement has been redone multiple times, with different distance indicators, by different teams, and it consistently gives the higher number. The discrepancy is real. Something is wrong, and the options are alarming. Either there is an undetected systematic error in one or both measurements. Some subtle bias that has survived all the checking, or the standard cosmological model is wrong. If the model is wrong, then our understanding of what the universe contains and how it has evolved is incomplete. The dark sector, dark matter, and dark energy, which dominate the model, might be behaving differently than we assume. Dark energy might not be a simple cosmological constant. It might evolve over time in a way we have not detected. Dark matter might have properties we have not accounted for. Or there might be something else entirely in the universe that we have not included in the accounting. New physics, new particles, new interactions. Something that affects the expansion history in a way that reconciles the two measurements. The Hubble tension may be telling us that our model of the 95% is wrong. That the universe is hiding something not just in terms of what it contains, but in terms of how those contents behave. This is shocking discovery number 6. The universe's expansion rate cannot be measured consistently by independent methods, suggesting our entire framework for understanding dark matter and dark energy may be incomplete. Shocking discovery. Number 7. Gravity speaks when nothing else does. For the whole of human history, before 2015, we observed the universe exclusively through electromagnetic radiation. Light in all its forms, radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays. Every telescope ever built, from Galileo's first crude instrument to the Hubble Space Telescope to the James Webb Space Telescope, detected photons. Electromagnetic radiation, the universe as seen in light. On September 14, 2015, the LIGO detector registered a signal lasting about 0.2 of a second. A chirp, a rising frequency followed by silence. The signal matched in extraordinary detail the prediction of general relativity for the gravitational waves produced by the merger of two black holes, each about 30 solar masses, circling each other at a significant fraction of the speed of light before colliding into a single, larger black hole. The merger had occurred about 1.3 billion light-years away. 1.3 billion years ago, two black holes that had been spiraling together for perhaps billions of years completed their final dance and merged. The energy released in that final fraction of a second, in the form of gravitational waves, exceeded the combined luminosity of every star in the observable universe. 3 solar masses worth of energy converted to gravitational radiation in an instant. That radiation traveled for 1.3 billion years through the universe at the speed of light, crossed the entire observable cosmos, and arrived at a detector in Louisiana as a distortion of space-time smaller than 1,000th the diameter of a proton. And we detected it. This opened a new era of astronomy, gravitational wave astronomy, the ability to hear the universe rather than just see it. Black holes, which emit no electromagnetic radiation at all, are invisible in every traditional sense. Neutron-star mergers produce gamma rays, but they also produce gravitational waves, and the two signals together carry far more information than either alone. LIGO and its partner detector Virgo have since detected dozens of merger events. The universe has a whole new voice we had never heard before 2015. But gravitational waves reveal something about the hidden universe that is crucial. Many of the most energetic events in the cosmos involve dark matter only indirectly, or not at all. Black holes and neutron stars are made of ordinary matter, but they are products of stellar evolution in dark matter halos. The cosmic web of dark matter influences the rate of galaxy mergers, and therefore the rate of black hole mergers. Every gravitational wave event is embedded in a dark matter context. More profoundly, gravitational waves pass through everything. They are not absorbed or scattered by dark matter or ordinary matter in any significant way. They carry information from the heart of events that are otherwise hidden. The interior of a neutron star merger, the geometry of a black hole in spiral. Physical conditions so extreme and so brief that no other signal could carry the information. The universe has been gravitationally whispering throughout its history. For 14 billion years, gravitational waves from billions of mergers have passed through the Earth without our knowledge. We built instruments sensitive enough to hear them only in 2015. An entire channel of cosmic information has been available and undetected for the entirety of human history. What else is the universe saying that we cannot yet hear? This is shocking discovery number 7. The universe communicates through channels we could not access until very recently, and gravity has been speaking to us throughout all of human history, with no one capable of listening. Let us take stock of what these 7 discoveries reveal together. The universe contains ordinary matter, the 5% we have spent centuries understanding, and it contains something like 27% dark matter and 68% dark energy. The ordinary matter itself has a hidden component spread through the cosmic web. The expansion history is determined by components we cannot see. The rate of expansion cannot be measured consistently by independent methods, suggesting our model is incomplete. And the universe speaks through gravitational channels we only recently learned to access. The cumulative picture is of a universe that is, by almost any measure, mostly hidden. Not hidden by choice or intention. Hidden simply because the universe's dominant contents do not interact with light. We are electromagnetic creatures in an electromagnetic civilization. Our eyes detect photons. Our telescopes detect photons. Our instruments detect photons of various wavelengths or particles that interact electromagnetically. We built our entire scientific understanding of the cosmos from one channel of information, the electromagnetic channel, and that channel reveals only 5% of what is there. The universe is not hiding from us. We are blind to most of it. This should be devastating to scientific confidence. It might seem to say that everything we have learned is worthless, that our best theories are hopelessly incomplete, that we are stumbling around in a darkness we do not even fully appreciate. But that is exactly the wrong conclusion. And here is why. The Voyager spacecraft, which we have talked about in a previous video, were designed and built with 1970s technology. Computers with 68 kilobytes of memory, transmitters weaker than a refrigerator light bulb. They have been traveling for nearly 50 years and have reached interstellar space. They have sent back data that revealed the edge of the solar system to be dramatically different from what every model predicted. What made Voyager possible was not perfect knowledge. It was imperfect knowledge applied with extraordinary care. Engineers who understood the limits of what they knew. Scientists who built models knowing those models were approximations. Instrument designers who created detectors for phenomena they predicted but had not yet confirmed. Voyager succeeded not because the scientists knew everything, but because they knew what they knew and built accordingly. The discovery that 95% of the universe is hidden is not a defeat for science. It is science working. The discovery itself is science. We did not always know about dark matter and dark energy. We discovered them by doing the right things, by measuring carefully, by taking anomalies seriously rather than dismissing them, by following the data even when it led somewhere uncomfortable. Fritz Zwicky measured velocities that made no sense and proposed dark matter. The physics community ignored him for 40 years. Vera Rubin measured rotation curves that confirmed the anomaly. The community took notice. Experiments were designed. The CMB was mapped with exquisite precision. Supernovas were used as standard candles. Gravitational lensing was used to map mass distributions. The evidence accumulated. The conclusion became unavoidable. This is how science is supposed to work. Not by knowing everything from the beginning, by discovering ignorance, taking it seriously, and designing new investigations to address it. The 95% we do not understand is not a failure. It is the agenda for the next century of physics. The experiments designed to penetrate the hidden universe are among the most extraordinary ever built. Deep underground, in mines and tunnels, shielded from cosmic ray backgrounds by thousands of meters of rock, detectors wait for dark matter to interact with ordinary matter. The Lux Zeppelin detector in the former Homestake mine in South Dakota uses 10 tons of liquid xenon cooled to nearly absolute zero, surrounded by instrumentation sensitive enough to detect the faint flicker of light from a single xenon atom recoiling from a dark matter collision. It has been running for years. It has found nothing, but nothing is a result. Nothing means that dark matter, if it is WIMPs, interacts with ordinary matter less strongly than the detector's sensitivity. Each null result constrains the possibilities. At CERN, the Large Hadron Collider has been smashing protons together at energies that recreate conditions of the very early universe, searching for supersymmetric particles that would include dark matter candidates. It has found nothing beyond the Standard Model. The Higgs boson was confirmed in 2012, completing the Standard Model. Nothing else has appeared. Again, null results are results. They have mapped out the terrain of failure and narrowed the possibilities. Radio telescopes are searching for the faint signal of axions, converting to photons in strong magnetic fields. The sensitivity required is extraordinary. The experiments are operating at the edge of what quantum mechanics permits in terms of measurement precision. New gravitational wave detectors are being built and planned. LISA, the Laser Interferometer. Space Antenna is a planned European Space Agency mission consisting of 3 spacecraft separated by 2.5 million kilometers, forming a triangle in space designed to detect gravitational waves at frequencies inaccessible from the ground. It will detect the mergers of supermassive black holes, the early universe's gravitational wave background, and possibly signals from sources no one has yet predicted. Pulsar timing arrays, networks of millisecond pulsars monitored for years with radio telescopes, have recently detected the first evidence of a gravitational wave background, a sea of overlapping gravitational waves from all the supermassive black hole mergers across cosmic history. The universe's entire merger history is encoded in this background. The signal was announced in 2023, and its properties are being analyzed for what they reveal about the black hole population and potentially about the early universe. The instruments of the hidden universe are being built and deployed. The scientific agenda for the hidden 95% is well defined. The experiments are running. The data is arriving, and somewhere in that data, possibly already collected and awaiting analysis, possibly in the next generation of experiments, possibly in an approach no one has yet thought of, is the answer. Here is what the hidden universe means on the scale that matters. Right now, at this moment, dark matter is passing through your body, not just through the room, through you, through every atom of you. The dark matter halo of the Milky Way permeates the entire galaxy. Every cubic meter of space in this galaxy, including the cubic meters occupied by your body, contains dark matter particles streaming through at hundreds of kilometers per second. The velocity distribution of the dark matter halo relative to the solar system's motion. In every second, something like 1 million dark matter particles pass through your thumbnail. If the dark matter is WIMPs, if the interaction cross-section is anywhere near the ranges that have not yet been ruled out, occasionally, very rarely, perhaps once in years or decades in the entire volume of your body, a dark matter particle glances off an atomic nucleus in one of your cells and deposits a tiny fraction of its kinetic energy. You do not notice. The interaction is too faint. Your body has no detector sensitive enough, but it happens. The hidden universe passes through you constantly. Similarly, dark energy is not something out there in deep space. It is the property of the space you occupy. The cosmological constant, if that is what dark energy is present in every cubic centimeter of vacuum, including the vacuum between your atoms, between your electrons and nuclei, between the quarks inside your protons. Space itself, right here, right now, is permeated with whatever dark energy is. You are not adjacent to the hidden universe. You are inside it. The 5% of the universe that is ordinary matter, the part that makes you, that makes the Earth, that makes the stars, is the minority, the exotic component, the unusual feature, in a universe made mostly of dark matter and dark energy. Ordinary matter is the strange stuff, the special case, the thin film of complexity floating on an ocean of something else. There is a philosophical dimension to all of this that scientists do not always discuss, but that is worth sitting with. Human beings have a long history of placing themselves at the center of reality. The Earth was the center of the cosmos. Then the Sun was the center of the galaxy. Then the Milky Way was a typical galaxy among many. Each step in the scientific revolution has been a step away from centrality, a demotion from whatever special position we imagined ourselves to occupy. The discovery that ordinary matter is 5% of the universe is perhaps the most extreme demotion yet. Not just that we are not at the center, not just that we are small, but that we are made of the minor ingredient. The universe's dominant components have nothing to do with us, nothing to do with stars or planets or chemistry or biology. We are an afterthought in a universe of dark matter and dark energy. And yet, we are the part of the universe that knows about the other 95%. The dark matter does not know it exists. The dark energy has no awareness of itself. The galaxies embedded in dark matter halos have no understanding of what holds them together. The 5% of the universe that is ordinary matter has produced, in at least one location on one planet around one star in one galaxy, the capacity to measure its own smallness, to discover that 95% of reality is hidden, to build instruments sensitive enough to detect the effects of what it cannot see, to construct theories describing things it has never observed. The fact that we are 5% does not make us insignificant. It makes us remarkable. The ordinary matter has, in at least one case, become aware of the ordinary matter's own minority status. The universe has, through us, discovered how much of itself is hidden from direct view. Vera Rubin spent years carefully measuring galaxy rotation curves, applying painstaking corrections, building a case from data that most of her colleagues did not want to hear. Fritz Zwicky measured cluster velocities with the instruments of his era and reached a conclusion that was correct and ignored for 4 decades. The teams that discovered dark energy were looking for something else and found the universe accelerating. The hidden universe was found by people willing to follow the data wherever it led. People who took anomalies seriously rather than explaining them away. People who built instruments capable of seeing what their predecessors could not see and made measurements their predecessors did not know needed to be made. The universe hides most of reality, but it does not hide it perfectly. It leaves traces, the rotation curves of galaxies, the velocities of galaxy clusters, the bending of light, the CMB acoustic peaks, the supernova brightness-distance relationship, the Hubble tension, the gravitational wave background. These traces are the universe's fingerprints on the hidden, the shadow of the dark on the light, the imprint of the 95% on the 5% we can see, and we have learned to read those fingerprints. The universe hides most of reality, and we are the part of reality that is learning to see in the dark. That is not a small thing. In a cosmos of dark matter and dark energy, and visible matter and gravitational whispers and invisible scaffolding, the emergence of creatures capable of noticing the hiding is itself one of the most extraordinary events in 13.8 billion years of cosmic history. The universe keeps its secrets, but it keeps them imperfectly, and we have been paying close enough attention to notice the gaps. What fills those gaps is the most important scientific question of this century. And the answer, when it comes, will redefine what we mean by reality itself.